Hi guys, I wanted to make another example where we did kind of a partial regression analysis. We haven't learned the full test yet, okay? But we are running this linear regression t-test. We're getting our variables and we are interpreting those. And then one thing I wanted to add to that was using your regression equation to then make predictions, okay? So we're kind of piecing it together little by little here. So what I have is a data set that compares temperature, and this is in degrees Fahrenheit, to the number of cricket chirps per second. So there is information that states that the temperature, as the temperature goes up, crickets will chirp more or chirp more quickly. So what we want to do is run a regression analysis to see if this is true. So the first thing that you have to ask yourself is which variable is independent and which is dependent. So the way I like to figure this out is by asking which one depends on the other. Does the temperature depend on the number of chirps per second, or does the number of chirps per second depend on the temperature? And in my mind, I think the number of chirps depends on the temperature. So chirps depends, so that makes it y. Temperature is what it depends upon, so it's independent, so it's x. So I'm just going to do it like this. Independent is temperature, dependent is chirps. So ideally what we want to do is we want to put our independent in L1 and our dependent in L2. So I'm going to pause the video to type these in. You can pause also and get these typed into your calculator to follow along. Okay, so I have my data typed in. I have temperature in L1 and chirps per second in L2. So what we want to do is run the tests so that we can find these different variables and ultimately get our regression equation. So we go to stat, we go over to test, and it's almost completely at the bottom, linear regression t-test. X is in L1, Y is in L2. We're not making any changes here. This will be when we learn the null and alternative hypotheses, but we are always going to leave it as not equal 0. So you can go ahead and anticipate that. We want to store our regression equation. So to do that, we go to vars, yvars, function, y1, and then we go down to calculate. So now what we have is our information here. So degrees of freedom, 13. One thing I do want to point out here, we had 15 pairs of data and degrees of freedom is 13. So now what happens is because we have two different pieces of data or two different things, two different variables, our degrees of freedom is now n minus 2 because we have two things to take into account here. So I'm going to scroll down and get A, B, R, and R squared. So I'm just going to copy these down. Okay, and I just kept them all to two places. Okay, now, in case you ever forget, on your calculator, when you run this linear regression t-test, it's going to give you the general setup for your equation. Now, they do not say y hat, but make sure we are always saying y hat. So it's y hat equals A plus bx. And the number that is with x is always your slope. So if you can't remember which is slope, which is y-intercept, remember the number that goes with x is your slope. I always like to think of it too of we've traditionally learned y equals mx plus b, where b is the y-intercept, and it's backwards now, okay? So what I want to do is I want to go through and I want to interpret all of these values. So A is my y-intercept. Okay, so my y-intercept means when x is 0, so when the temperature is 0, the number of chirps per second is negative 0.31. So this is one of those cases where your y-intercept is actually not meaningful, because one, if the temperature is 0, there's probably not going to be any crickets out, and two, a cricket cannot chirp a negative number of times per second. Okay, my slope is b. So your interpretation for slope is for every 1 unit increase in x, y will have this many unit increases. So for every 1 degree increase in temperature, the number of chirps per second increases by 0.21. Okay. Now we have r and r squared. R is our correlation coefficient. R squared is the coefficient of determination. So correlation coefficient R. This is the one that was on that scale from -1 to +1. 0 is no correlation. 0 to 0.2 is weak. 0.2 to 0.8 is moderate, and 0.8 to 1 is strong. So 0.84 falls in that strong category, and it's positive. So this shows we have a strong positive correlation. And r squared is your coefficient of determination. So this is given as a decimal, but we want to interpret it as a percent. So this shows the percent of variation that is explained by this linear relationship. So what we would say is 69% of the variation in chirps per second can be explained by the relationship between temperature and chirps per second. Okay, so we're saying that this relationship is strong enough that 69% of the variation that we see in chirps per second can be explained by this relationship. So I mentioned in a previous video, there are always external factors. So you will pretty much never see 100% of the variation explained by the relationship, because there's always these other external factors. But we have a pretty large percentage. So one thing that I want to do is I want to look at this because we said it was a strong positive correlation. So I want to turn my scatter plot on.
Which one is bothering me?
Okay.
It's cold.
Sorry, we had a hearing aid crisis. So I've got my plot turned on. I've got scatter plot, XL1, YL2. I want to go to zoom stat. And because we stored that regression equation, it's going to go ahead and put the line of best fit in there for us. So I agree, moderate to strong, pretty good. Everything stays kind of hovered around the line pretty well. So that's good. So now, one of the things that I want to kind of explain again is with this picture, the dots represent the actual data values. So I can trace on here. So when it was 88.6 degrees, there was 20 chirps per second. When it was 93 degrees, there were 19.8 chirps per second. 80 degrees, 17.1. So these were the actual values. Now, what happens, let me get to a point where there we go. So right here at 84 degrees, we saw 18.4 chirps per second. Now, if I hit my down arrow, I'm now on the line, and I want to go to about 84. So when we recorded data at this 84 degrees, we saw 18.4 chirps per second. but our model predicts that we should only see about 17.5 chirps per second. So this shows you the difference in the actual values and then the predicted values. So the line represents the predicted values. Okay. So there's a couple of different ways then that you can do question number 3. Predict the number of chirps per minute when it is 75 degrees. So we have this equation that says y hat equals negative 0.31 plus 0.21x. So going back to our table, we labeled temperature as X. So when they give us this temperature of 75 degrees, that is an X value. And what I could do is I could plug this in and then I could evaluate it to get a predicted value. Okay, so if I type that in, negative 0.31 plus 0.21 times 75, I get a y hat of 15.44 chirps per second. Now, going back to my graph, another way that I could do this, I'm going to make sure that I hit trace, and I want to be tracing the equation, not the plot. Now, we've done this before. We did this in finite, is if I have my line being traced, I can type in anything that I want for x. And then I can hit enter and it's going to give me the corresponding y value. So it's going to show up on this line and say when it is 75 degrees, here's the line. Here is the predicted number of chirps per second. Now you notice we have a little bit of a variation in our answers, and that's because here I rounded these values, but here, because I told the calculator to store the equation, nothing got rounded. So this is actually going to be a more accurate answer, and I would suggest trying to do this on the homework, so that we're not missing questions for rounding. So I'm going to say y hat equals 15.58 chirps per second. Now, if you do this on the homework and you do it this way, that's fine. If it counts it wrong and you are pretty certain it's just a rounding issue, just email me and I'll go in and manually check it and fix it. Okay. But now at this point, you should be able to do homework number 1. So I'm going to open that up to you on my Open Math.